Okay, so the starting question, I will start by explaining you what are these meandric systems and what are the questions we have considered on them. So the problem takes its root in enumerative geometry. So you know enumerative geometry, you look at some kind of geometric structure and you want to classify it and possibly count them. So we've seen discussion on ramified covering of the sphere. Knot theory is also, in some sense, you have a closed curve, simple curve in the space. And here we look at something different. We look at two closed simple curves in the plane. And what is interesting is somehow how they intersect, okay? And we want something rather generic. So we will take things with no multiple crossing points, with no tangent points. And the problem is to try to classify this kind of structure. So of course, one clear invariant is the number of intersection points. If you do continuous deformation, you don't change that. But with a given number, how many such configurations are there? So like this, it looks really like a geometric problem, but we'll see in the next slide that it can be translated in a much more combinatorial problem with some non-crossing matching, so objects we are more familiar with in this community. So that's a picture of two such curves. And just to show you that this question has appeared already, has already some long history, this is a picture from an article from 1912 of Henri Poincaré. And here he was looking for some reason as this kind of configuration on an annulus. So that's why you have a small inner circle and this outer circle. But the configuration is really what is between the circles. And you see that we have these two non-crossing curves intersecting generically. Okay, but I will more use picture like that. And even I will have a more combinatorial picture in a moment. So when you do combinatorics and numeric, we all know that it's rather painful to have symmetries and unrooted objects. So the first thing you want to do is to consider more rooted objects. And in fact, what is called a meanders is such a configuration of two curves, but rooted. And rooted in which sense? In the sense that you distinguish, so here an intersection point, but not only the point, you will choose at this point one of the curve and a direction. And once you do that, obviously you can follow the curve that you have distinguished and you can number your intersection point from 1 to n. So here it will be 8. And since we are interested into configuration up to deformation, what you can further do is imagine, for example, that you cut your first curve here so that you can transform it into a line. And then the configuration will look like that. And if you don't like, cutting is not really something which is deformation, which is continuous deformation. But if you don't like that, you can imagine that it's closing somewhere like that. Okay, so this is much more combinatorial, as you can see, and that's the object which is called a meander. So if I translate that completely combinatorially, what you see is that you have this straight line with number from 1 to 2n, so there is no information there. The information is what you see above and below. And on each side, what you see is simply a non-crossing pair partitions. Okay, so a meander is just a pair of non-crossing pair partitions, but there is an extra condition. Okay, this thing which is not the line should form one single closed curve. So said otherwise, I need that when I look at my two non-crossing partitions together, the graph they induce is connected. Okay, and that's what makes, of course, the problem difficult. This is really a condition which intertwine my two non-crossing partitions. So first question you can ask, and we want to ask as enumerative combinatorial, is how many configurations of that kind with 2 on 2n points they are. And this turns out to be a difficult question. So of course, if you don't have this connectedness condition, the answer is very simple. We know, I don't know the number in Stanley's book by heart, but we know that non-crossing pair partition are counted by Catalan numbers. So you have Catalan number square. And first thing we would like to say is, okay, connected, I need to do some generating series and take the log, but that does not work. Why? Because if you think a bit at a general configuration with two non-crossing matching, the connected components can really a bit interact in a strange way. They can, and you don't have, it's not a set of connected components. You have extra information, and we don't know how to put that in a generating series. And it's probably, if it's possible, it's probably very complicated, and you will see why I say that in the next slide. So just to sum up a bit, what we said, it's easy to show that the number of configuration on two endpoints is smaller than the Catalan number squared. It's also easy to show that it's at least the Catalan number, because it's a small exercise. If you have one non-crossing matching on the top, you can complete it in a connected fashion so that the thing is connected. So in particular, it grows exponentially. But what is the exponential growth, and what is, we like to think when it grows exponentially, if things are going well, it looks like that, like a constant times exponential growth to the n and n to some singular exponent. And that's where the story starts to be fascinating, is that, so we have some numerical approximation for the growth rate, but there is no precise conjecture. We also have some numerical approximation for the singular exponent. And here there is a precise conjecture, and the precise conjecture is rather amazing. So the conjecture done by DiFrancesco, Linelli, and Gitter in 2000 is that this singular exponent is 29 plus square root of 145 over 12. And this, the story is rather interesting. I mean, so the first computation of this singular exponent was done, I think, by maybe Landau and Swankin. I'm not sure exactly what they were for. So in the early 19th, and they had a few, they computed Fn for a few value, and they did some rough numerical approximations. They find 3.4. And as everybody will say in that situation, they conjecture that it's 7 over 2. And then people computed a more value using more sophisticated tool to estimate the exponent. And they say, oh, it seems to be really 4.442. And then there was this paper where they say, okay, we assume that meanders are related to quantum gravity with central charge equal -4. So don't ask me what I need. And from this assumption, we compute this critical exponent, and it matches up to 4 digits the known numerical estimates. But okay, nobody, I think, nowadays has a clue on how to prove this conjecture. And when you have now such a nice conjecture and you have no clue how to prove it, what you do is you keep it as a good advertisement for your talk, but you look at another question. So that's what we will do today. And we will look at this question following some paper of Goulden, Nika, and Puder, as I said at the beginning. And what they suggest is the following. So, okay, what is very difficult is this connectedness question. So we will remove this connectedness assumption, and now we have a very simple object, and we call just it meandric system. It will be just a pair of non-crossing pair partition. And the idea is that as for meander, you draw one of them above a line, the other below the line, and you will look at the components that they form. Okay, so counting meander is evaluating the probability. If you imagine you take that at random, the probability that you have only one connected component. And another question you can ask is, what is the typical number of components? And so what they suggested in this paper, and they had some lower and upper bound for the expected number of connected components, and both are a constant time n. So the lower bound in their paper is 0.17 times n, and the upper bound 0.5 times n. And the question is, when you see that, is if you take the expected number of components, divide by n, does it converge, and what is the limit? Okay. And what we could prove with Paul Tevna is that indeed, if you take the expected number of components and divide by n, it converges to some number kappa. So I will comment what is kappa in a moment. But in fact, we have a bit more than that. You see here, there is no expectation. So you can really look at the number of components as a random variable, and it converges in probability to kappa, which means that, okay, it's concentrated around kappa times n. Something which is interesting, so we don't have a very compact formula for this kappa. I will show you some rather complicated summation, combinatorial summation formula at the end, but it's defined in terms of something which appeared recently in some probability paper by Curien, Kozma, Sidorovicius, and Tournier, which is called the infinite model. So I'll say a word on that in the second part of the talk. And we could also, using this description, we could also improve somehow the bound on the constant, and that's our bounds, and you can compare. So numerically, if you do numerical estimate, it's supposed to be around 0.23, and we can say that it's between 0.2 and 0.3 roughly. Okay, so that's what I will explain. In fact, the proof is not that, or at least the idea of the proofs are not that complicated. So I will give you really in the second part of the talk the main idea of the proof. But before doing that, I would like to mention that this theorem has also a nice interpretation if you look at the lattice of non-crossing partitions. And this was explained in the paper of Goulden and Nika and Puder, that it's equivalent to look at this question and at some question in this lattice. Okay, so I forgot to say that. So, and the idea is that you can, so I will not redefine what is non-crossing partition. I think most of you know, and if you don't, you will be able to follow the rest of the talk. Anyway, it's somehow a parenthesis. And so you know that non-crossing partition, you have an order structure on them by refinement. And then you can consider the Hasse diagram, which is the graph of cover relation in this poset. And so this is an oriented graph, but you can forget orientation. And then you have a notion of distances in this graph. And in fact, there is a way to send, so non-crossing partition, it's known to be in bijection with non-crossing pair partition. So non-crossing partition of n with non-crossing pair partition of size 2n. And if you take two non-crossing partition, you can associate to it a meander such that the distance in the Hasse diagram is related to the number of components of the meander. And because of that, the theorem that I just stated, which says this is concentrated around kappa times n, tells you that this distance is concentrated around n times 1 minus kappa. So say otherwise, if you take two independent uniform non-crossing partition, you divide by n their distance in the Hasse diagram, this tends to 1 minus kappa. And just to give you an idea, maybe because if it's a bit abstract, if you want to imagine, to picture yourself what it means to have a graph, a large graph, where when you take two vertices uniformly independently at random, the distance concentrates to some value. A typical example will be a high dimension hypercube. So in a high dimension hypercube, dimension 2, you take two vertices at random, they are roughly at distance d over 2. And somehow this says that asymptotically, the geometry of the high dimension hypercube has some commonality with this Hasse diagram of NC of n. Okay, so that's the end of the parenthesis on this Hasse diagram of non-crossing partitions. And now I will go to the second part of the talk. I will tell you the main idea in the proof of our main result, and we'll see what is this infinite model, this funny name I mentioned, and why does it come into play in this talk. Okay, so in fact, the proof starts with a very simple observation. Somehow I called it lemma, but you will see the proof is two lines. It's very simple, that you can interpret give somehow a probabilistic interpretation of the number of components of M divided by a meandric system divided by n, and here it is. So here, for the moment, I don't consider a random meandric system. That can be any fixed meandric system of size n. what is random is this lemma is this I sub n, and it's the most easy random object that you can imagine. It's just a uniform random integer between 1 and 2n. So I want really to think at that as a uniform point in my meandric system, okay? And now when you have a point in a meandric system, you can look at the components which contains that point. And that's what I denote by C sub I of m. And I take the size, okay? The inverse size, in fact, and the expectation of the inverse size. So here I insist the expectation is with respect to this, to taking a point at random. And this expectation is just up to a factor 2, the number of components divided by n, okay? And okay, I could have left that as an exercise, but we have already homework from this morning talk, so I will give you the solution for that one. And it's very easy, as I said. So you just write down explicitly what means expectation. Here we have a uniform random element, so it's just 1 over 2n times the sum. And in this sum, you can observe that each connected component contributes 1. Okay, you have, okay. We know this kind of argument. So that's it. Okay, and now, just before telling you why I'm interested in this small lemma, I will take the expectation. So now here I said M can be any meandric system, and just only I is random. But now I will put M random also. So let M sub n be a uniform random meandric system. I take the expectation on the left-hand side, so I get that. And here on the right-hand side, I have some kind of double expectation. So it's just an expectation. But here, the difference is that now both Mn and I sub n are taken at random and uniformly and independently from each other. So if you want, you can think I have, since I told you I want to think as I as one of the points in my meandric system, I have a random marked meandric system, okay? So why is that interesting? It's interesting because somehow it changes a global question, and global things are typically difficult. These things of, having one connected component was really hard in the problem of counting things, into something more local. What I mean by that is that, so here it's a bit hand-waving to give you some idea, and I'll be a bit more precise a few slides later. What I mean by that is that if I tell you, okay, I have some meandric systems, and here you have your marked points, and you see only a bit of the meandric system, okay? If I tell you that, and I ask you what is the number of components in the meandric system, you have no chance to answer that. But if I tell you what is the inverse size of the component containing your marked points, maybe you'll be lucky. And maybe it looks like that, and you can answer the questions. Or it's the inverse size. So maybe you don't see the whole component, but you see that it has already many points, and you can answer approximatively that, okay, you don't know exactly what is the inverse size, but it's small. And in fact, I said maybe we'll be lucky, but what the proof says is that we will be lucky most of the time. And so this is, in this sense, this 1 over the inverse size of the component is something local. So if you want to tell how does this expectation of inverse size of the component look like asymptotically, what you should do is tell what does a meandric system, a marked meandric system, look like locally around its marked point asymptotically, okay? And that's what we did. So in probabilistic terms, you want to find what we call the local limit of these marked meandric systems. Okay, so I will give you an intuition of what this local limit is. In fact, it's not very complicated. And here we have something that we all like. We know that this non-crossing pair partitions is in bijection with Dick paths, okay? Which means that if I take 2 non-crossing partitions, I have a bijection with a pair of Dick paths, so I drew it one upside down so that the picture looks a bit more pretty. And now we said we have a marked point, and we want to see what things look like around this mark point. So this means I have a mark point somewhere in my pair of dig path, and I would like to see how do the dig path look like around this point. And there is a very simple and not too difficult answer to that, is that in fact, when you look around a mark point and the mark point is taken uniformly at random, the dig path will just look like an unconditioned random walk. So the idea is, okay, a dig path is just a random walk, so which is conditioned to come back in 0 at times n and to stay always above the diagonal. But if you look locally around a point in the middle, this point will be at height square root of n typically. So if you just look at a few steps on each side, you have no chance to go below the line. So you can forget this conditioning to go below the line. And basically, the fact that you have to come back at 0 at times n, that's far, you can also forget about this condition. So what we have here now when we look is just a pair of random walks, so bidirectional random walking goes in 2 directions, but with completely independent step and no condition. And this means that now we would like to come back to the picture of your meandric system. What does the meandric system look like? It's just you have the bijection between your matching and dig paths, and now you just have to revert it and apply it to random walk with independent steps. So I will be more precise. It looks like that. So you start with 2 B-infinite sequence. So instead of drawing path, here I draw arrow. If you want a right arrow, is just an up step, and left arrow is just a down step, but it's more natural with arrow for what I want to say. And all this symbol, so you have 1 symbol in each position and 2 symbols in each position, 1 below, 1 above the line. And all these symbols are independent and just probability 1/2 for each chance. And now from that, what you do is that you connect left to right arrow. And it's very easy to see that you can only connect it in a unique non-crossing way. Okay. And okay, here of course, I cannot do B-infinite picture. So there will be things which are not connected in the restrictions that I show. But in fact, it's a simple lemma to show that everything is connected at the end. So you always have a right arrow matching this left arrow. Okay. And what you get like this is what is called the infinite nodal. So not exactly what they call infinite nodal, is more the potentially infinite components there, but I will call infinite nodal this picture. And it was in fact introduced in this paper recently by several authors. So it's interesting to run also into this object. Okay. So now I told you this is at least intuitively the local limit of our random mark meandric system, but here that's a formal statement. So what we proved, but in fact it was almost in terms of dig path, once it's rephrased in terms of dig path, that was somehow already in the literature, is that if you take a uniform marked random meandric system, it converges locally in distribution, so that's random objects, so we have convergence in distribution, to this infinite nodal, which is marked in 0. Okay? And what I mean by converge locally, it means that if you fix yourself a width, a radius r, and you look at the restriction of your marked meandric system on the marked point, r point on the right, r point on the left, then this is just a discrete object. This lives in a finite set, and the probability of each configuration will tend to the probability of the same configuration in the infinite nodal. So this is something very, very concrete. When you look in a fixed window, it converges. Okay, and so now we're happy with that, but what we wanted is not the convergence of this marked meandric system. We wanted to look at this expectation of the inverse size of the component. And we studied a bit to do that. What we do is we look really at this inverse size of component as a functional on the set of meandric system. And what we could prove is that it's continuous. So it's not continuous on the whole set of meandric system. you need, it's continuous on some subset. The subset of what we call complete Mark meandric system is where each point is linked to another point. So why is there this? When you start to take restriction, it might happen. So I did a bad picture here because I don't have that, but it might happen from time to time that when you look at your restriction, you have some arcs, you don't know where it's going because it's going outside your window. So we have to define local convergence, we had to extend a bit our space and to admit that sometimes you have not pairs, but you have singletons. And when you have singletons, we know whether the arc is going to the right and to the left, but we don't know where it's going, okay? And if you have this kind of thing, you might have some problem of continuity. But if you don't, if it's on the set of complete Mark meandric system, the functional is continuous. And I told you when I introduced infinite noodle, it's an exercise to check that there everything is connected to something else. So this means that with probability 1, the infinite noodle lives in this set of complete Mark meandric system, and this continuity, even if it's not on the whole space, it's enough for what we want to do. Okay, so that was a bit a technical argument, but now we can put together, and we'll see that we won't have directly like that the proof of the theorem that I announced, but we will have a weaker version where we only have convergence of the expectation. But okay, that's already something, and I will comment on how to get the stronger version later. So if I recap a bit what I said, we said that this Mn, In converge to the infinite noodle, that this map is continuous on complete Mark meandric system, and that this infinite system is complete with probability 1. And when you have that, it's a classical thing, which is called the mapping theorem, that you can apply to this. You can apply your almost surely continuous map to this convergence in the first line. And what you get is that the inverse size of the component of In Mn converge to the inverse size of 0 in the infinite noodle. So this is more our constant kappa, or maybe no, sorry, I missed a function. This is a random variable for the moment. And then what we are interested in is the expectation of this thing. So we will take expectation is this convergence. There is no problem. They are bounded random variable, and we have this, okay? And the left-hand side, that's what I explained at the beginning, is just 1 over n times the expected number of components. And the right-hand side, we don't really know what it is, but it's some number, and that's what we will call kappa, okay? So we don't have a formula for kappa, as I told you, but we have a probabilistic interpretation, and I discussed a bit further what we can say on this kappa. Okay, so that's just a small comment here. Something which is interesting is that here, this component of 0 in the infinite noodle, it might be infinite. So we don't know whether it's finite almost surely or not, but the nice thing is that in this continuity result, we don't need to know if it's finite or infinite. And the proof go through even if we don't know. I think I said that more for myself because we were a bit worried that this would be a problem when we started to think about the problem, but it's not. So that's the weak version where we only have convergence of expectation. Just a word about how we get the strong version. So here you need to consider random measure and convergence of random measure. So that's always give me a bit of headache. But in fact, just to tell you very roughly, we have to get the concentration of this number of components, we have to prove a stronger version of this local limit convergence towards the infinite noodle. And in this stronger version, what you do is that you don't take your meandric system and your points simultaneously at random, but you first, if you take a meandric system and you think at all positions where you can mark your points, this already defines you a measure on the set of meandric system. And when you take the of marked meandric system, and then you have a random measure if you take M as random, and we prove convergence of this random measure. And then you have a random measure version of this mapping theorem we were using, which is also rather gives a headache when you start to state it and to write it. But we were using some results. There is a big book about random measure by Kallenberg, and we were using results from there, and we could, and this works without big difficulty, I would say. Okay. So last section, I would like to tell you a bit more about the constant kappa, because I mentioned some bound. Perfect. And because also there is a nice combinatorial formula, in fact, in terms of meanders, of not meandric system, really meanders. And there are nice things appearing that we don't really understand. You will see. So first, just because this is still more probabilistic, but I find that rather pretty. I told you this kappa in terms of the infinite nodal, it's twice the expectation of the inverse size, but it has also a more compact probabilistic interpretation. It's twice the probability that 0 is the leftmost point in its component. Okay, so and this is, it's not very hard to go from here to here. It's just a simple translation invariant argument. I won't detail that. But the nice thing is that if you think, so you have your infinite nodal, so meaning you have 0 somewhere, you have some row above and below 0. And if you want 0 to be the leftmost point, it means already that this arch should go right. And this one also should go to the right. And this has probability 1/4 to happen. So this gives you already a bound. Sorry, it's here that your kappa is smaller than 1/2. And you can make that a bit stronger. Maybe if I want that 0 is the leftmost point in my component, I should avoid configuration like that, where I have some, let's say, small arch, another arc like that, and then I have a big arc going left. And if you try to describe configuration like that and avoid that, you can improve your bounds. And that's basically the idea on how we get the upper bound in the theorem. And okay, now that was more probabilistic. I promised you also some more combinatorial description of kappa. And here it is. So the idea is that, so kappa is the expected inverse size of the component of 0. And what we will do is say, so if we will look at what is the possible shape of this component. So it can look like that, with something in the middle, something here, something here. And so that's the case where the component has size 2. And if you want it to look like that, what you need to have is have some non-crossing matching here. Non-crossing matching, and another one below. Okay, and then you need also to have a right path here, a left path here, a right path, and so on. You need to have a row in good direction in this point. And you can write down precisely what is the probability of that to happen. And if you want to do that for more complicated shape, what you need to do is to, for example, if you want to look at the probability that component of 0 is this shape, here you need to put a non-crossing matching in what we call the face F1, a non-crossing matching in F3, a non-crossing matching in F2, and so on. And what we get at the end is a big formula like that. So kappa is a large sum over meanders. So here is K is the size of the meander. Here, that's a notation for meanders for us. So 1 means that there is one connected component. And of some quantity, which will be a large sum like this of Catalan numbers. And the Catalan numbers comes from the fact that you have non-crossing matching that you put inside faces. And we started to try to compute a bit this probability, and there are funny things which happen. For example, so if you look at this thing, I told you you have two non-crossing matching, so that's what you have a sum of Catalan of L squared. The L will be the distance between these two things. Times, okay, this is basically, you will look at the series of Catalan square number at the radius of convergence. And it turns out that, you know, there are some mathematical way to compute that, which are implemented, for example, in Mathematica. And Mathematica tells you it's equal to this strange rational function pi. And this goes a bit further. So if you look at some shape of size 4, you still have things which is a rational function of pi, but this does not look to be the case later. And in general, we have no idea how to compute this kind of large sum with product of Catalan numbers, but where you have sometimes some repeated indices and things like that. So if you have some insight on this sum, that would be interesting. And okay, I'll just, since I have 1 minute, maybe 1 minute and a half, I just come back here to say, so this is a kind of combinatorial formula. So we're happy, but it's a very complicated one because, okay, I said first you have a sum here over meanders, and I told you meanders, we have no idea how to really enumerate them or generate them or some things like that. So it's a complicated sum. And even for each meander, if you, for small meander, we can compute this sum, but for larger meander, we don't know how to compute this sum. So it's still, okay, it's combinatorial, but it's still complicated. But what you can do, if you want just some lower bound on kappa, is truncate everything. You better use a computer, so that's what we did, and we truncate this sum. We just look at meander until I don't know if it was size 8 or 10 or something like that, and that's how we got the lower bound on kappa. Okay, so I think I'm done. Thank you for your attention.
My mic's on now. Yeah, yes, Sergey.
So from the bisection you mentioned at the beginning, do I understand correctly that counting meanders is equivalent to counting pairs of non-crossing partitions that are at the maximum distance in the diagram?
Yeah, I think it's okay. But that's in the undirected Hasse diagram. I can repeat it if you want. So,
sorry. Oh yeah.
Yeah.
Okay, for the people. Okay, good.
So there is this bijection between pairs of non-crossing partition and meandric systems, which change the distance in the Hasse diagram of the non-crossing partition to n minus the number of connected components. And meanders are the meandric system with one connected component, which means there are also the pair of non-crossing partitions, which are at distance n minus 1 in the Hasse diagram, and n minus 1 is the maximal distance we can have in this Hasse diagram.
Are there any other questions? Joel.
So the concentration result says that the window is little o of n, basically.
Yeah.
Everything's inside. Do you have any idea how wide it is? Where like you get an actual?
Yeah. So there is. Yeah. So the question is, we have proved that the number of components is typically kappa n plus little o of n, and how does this little o of n behave? And in fact, it was on the slide, and I jumped to the other slide and forgot to say it. So there is another article on random meandric system, which was done independently of the one of, I think it was a bit after the one of Goulden, Nika, but from Kargin, and he does not seem to be aware of the work of Goulden, Nika, and Puder. And he did some more numerical simulation, and the numeric suggests that this number of components is asymptotically normal with a variance which is also linear in n. And in fact, heuristically, our proof seems to suggest that also, but we cannot prove it. So the idea is that at least when you look at order n, what our proof says is that most components, or the leading term is really component of small size and also small width, which, and for the size of the component, and we look at component of that side, we can prove that there is a central limit theorem for that, so that it's asymptotically normal with linear variance. But the thing is that we don't have any control of like a component of size n to the 1/4, and there could be n to the 3/4 of those. It does not seem very likely, but we don't know how to say that it's not the case. But yeah, the conjecture is that, and I really believe it holds.
Are there any other questions? Okay, so the next talk will be in a couple minutes. So just get set up. Let's thank you. Thank you.